Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this lecture is entitled Yet Another Fundamental Theorem of Calculus, FTC2. Here's a statement. So if f of x is continuous on the closed interval AB, then g of x, defined to be the integral, the definite integral from a to x, f of t dt. Notice that the x is in the upper portion of the integral only. It's the upper limit. So this function g of x equal to this is continuous on the closed interval AB and is differentiable on the open interval AB. And if you take the derivative of this with respect to x, you get the integrand evaluated at x. So g prime of x is equal to f of x. Now, an alternative notation for this derivative portion of this theorem is the derivative with respect to x of the definite integral from a to x, f of t dt, a is a constant, is equal to f of x. We're going to look at the proof of this just briefly because it reminds us of many things that we've studied already. So first of all, what we're going to do is we're going to take a difference quotient. So here is the difference quotient that we're going to take of this function called g of x. And then we're going to take the limit as h goes to 0 of this, and that's going to be the derivative. So we start here and suppose that x and x plus h are in the closed interval AB, and so if we subtract those two, we get this minus this. So what we can do then is we can rewrite these integrals by taking a point in between, and x is certainly in between a and x plus h by definition, and so we can group those together. And that will tell me that this really is going to be, because those are going to cancel, just the integral from x to x plus h f of t dt. So we now can compute this. So we have this is what that difference is divided by h, and we have this. But now we have the extreme value theorem, which tells us that since f is continuous, there are, it achieves its max and mins on the closed interval AB. So we let f of c equal the minimum and f of d equal the maximum, and we call those little m and big M respectively. Then we have a property knowing that this integral is bigger than this and less than this. Or said another way, it's like this. And what I can do is divide both sides by h to get this. But this is nothing more than this difference quotient. So it's between f of c and f of d. Now, we can go through the same argument if h is less than 0. Now we take the limit as h goes to 0 of this. And what happens is the limit as h goes to 0 of c is f of x. The limit as h goes to 0 of d is f of x. Because of the continuity. So the squeeze theorem applied to this tells us that this limit, which is the derivative, is f of x. So you see we've shown that g prime of x is f of x. So g of x is differentiable on AB. But we know that if it is differentiable, it is also continuous on AB. But if we take the limits, we can go through similar arguments and conclude that it's continuous on the closed interval AB. And that's the end of the proof. So here's a problem. I want you to give it a go. This is using that theorem. So you take the derivative of each one of these. You know what to do. Let's see how you did. Well, the first one is straightforward. A is minus 4. That's a constant, and the x is up here. So the answer is g prime of x is just, I substitute x in to the integrand instead of t, and I get this is my answer. The next one is more complicated because it is different. We have x squared, and we also have x squared on the bottom, not the top. So let's begin considering this. So if we take the derivative of this, I can say, well, the theorem tells me about being on the top, so I can switch the limits of integration and call this the derivative with respect to x of the definite integral from 1 to x squared of the same thing. I'm using one of my properties. And then this constant will factor through the derivative, so I will get this. But now we've got to think about the chain rule, because you see I do have a constant at the bottom, but I don't have x up here, I have x squared. So you see I'm having x being mapped to x squared, and then x squared is being mapped to this integral. So the chain rule really is operative. You see the fundamental theorem of calculus we just talked about requires an x in the upper, and we've got x squared. So to take this derivative, we need to use the chain rule this way. We're going to be multiplying by du dx. So if u is equal to x squared, we get this. This was equal to this, but now we're letting u equal x squared. So this is going to be the same as the derivative with respect to u, which is going to have u be substituted into the integrand, so it's minus that, but then times du dx, that is 2x. So then this is going to be minus 2x that way, times this, but now I'm going to substitute what u was back in here, and everywhere there is everywhere where there is a u here, I'm going to put x squared, so I will get this, and when I simplify it using properties of exponents, I get this. Now, using the chain rules we did in the last part of that example allows us to derive some more complicated formulas. Certainly, if I'm integrating from a to u of x, then it's going to be put the u in for the integrand argument, but then take u prime of x. But we could also do it for a bottom one, and if for the bottom one we again did this, but we just turn it upside down, and so we get this, minus v prime of x times f of v of x. And we could also break up both limits going this way and to pick a point A that's either between them or not between them, and I can take this derivative, and when I do, taking the derivative of this one and the derivative of this one, combining them, I get this formula. Now you don't have to memorize that formula, but what you can do is break the thing up and try that. Let's attempt a problem. So this is example 7. You know what to do. Let's see how you did. Well, just using the formula we have, what we're doing is we're breaking this up. So we're going to be subtracting the bottom thing from the top thing. So when I take the derivative of this, what's going to happen is I'm going to get, at the top, I'm going to get, let's see, that's, the top is over here. And so at the top of what I'm going to do is I'm going to substitute 3x into all of this. So I get 3x squared, sine of 1 plus 3x squared, but then it's times du dx, so that is the 3. And on the bottom, and there's where the minus sign comes from, it is going to be the square root of x whole squared times sine of 1 plus the square root of x whole squared. But then I have to use the chain rule, so it's the derivative of that, which is minus 1/2 x to the minus 1/2. There is a minus there. And if we simplify this expression, this is what we get. Cool, huh? In closing, now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless.